For problem 3, we will have a conductor. We will have cylindrical shell with inner radius A and outer radius B. This is side view. For the side view, I'll just draw it A and B. The length of this wire is L. The resistivity is constant. Rho is constant. It's a given number, and this time is constant. Somehow, a known current I is made to flow radially out like this, from inner shell to outer shell. This is side view and this is current. So current is flying in radial direction from inner shell to outer shell. What I need to find the resistance R of this shell to the flow of the current. So we are finding this is given, and we need to find the resistance of this wire. Okay, so looks like a simple problem. We write R as rho L over A, and now the trouble begins. So if you look at this side view, we will immediately understand that area is different. It is different here and here and here. It's changing. So obviously, to find R, we need to integrate. So what we will do, we will consider some arbitrary surface of radius little r. And we will write the resistance dr for this infinitesimal shell. So what is dr? For this little r, for this shell of radius r, infinitesimally thin, it is rho, that is constant within it, length in the direction of current's flow. So it is, I will draw it as infinitesimal, thin, thin, thin here. So what is the variable of integration? The variable of integration length is in the direction of current flow. Current flows this way. So this is our depth, which is dr. So it is rho dr divided by cross-sectional area A. So what is cross-sectional area of the cylinder? It is 2 pi little r for this shell that we choose, arbitrary infinitesimal, 2 pi r, and the length is L. So this is our dr. And if we know dr, now we can integrate and write that r is integral dr. We need to integrate from A to B, integral from A to B dr. It's integral from A to B. dr is rho dr divided by 2 pi r L. It is equal to, rho is constant, 2 pi L constants, dr over r is logarithmic function, and the limits are from A to B. So we plug in the limits and we get rho over 2 pi L, then logarithmic function B over A, and this is the resistance of this cylindrical shell when current flows in the radial direction. Now, what if instead rho being constant, I will give you rho as a function of r. Rho as a rho changes now with radius. It is rho naught r over b, where r is in radial direction. Do you know what to do? Yes, of course, because now what you have to integrate, this rho will not be constant anymore. It will be just part of your integration. So r will be again integral from a to b dr, and dr will be rho, that in this case is rho naught r over b. This is rho, then dr divided by 2 pi rl. This is equal to rho naught over 2 pi bl, and then integral dr over r from a to b. And I lost this r, which is not a good idea. R dr over r. R and r cancel out. So we have rho naught over 2 pi bl. Integral dr is just r, and I plug in the limits. It will be b minus a. So we found the resistance of this spherical shell if rho changes with r. There is another way to think about this problem, so let's come back for rho constant. Resistivity is constant. Again, I'm looking for the resistance of this shell. So we will find first the difference in the electric potential between two radii, V at B minus V at A. It is equal to minus integral from A to B E dot dr. E is rho j. We keep going. So it is minus integral. Electric field, current is in radial direction. Then J is in radial direction. Electric field is in the radial direction. So E dot dr is just product E times dr. And E is rho that is given, J, and then dr. The limits are from A to B. Now, what is J? J is at that particular R that we choose. J is current divided by the area of this cylinder. So we are now consider some arbitrary cylindrical shell at radius, arbitrary radius r. So the surface area will be 2 pi rl. This is J at that particular area, and we understand that we cannot just write it as B minus A. That would be a mistake to write R as B minus A because it's changing with radius. We need to integrate. So it is, we bring it here, it is minus integral from A to B rho, that is constant, J that is changing, it is I divided by 2 pi rl rho j dr. Now we take this integral, it is minus rho I divided by 2 pi l. dr over r is logarithmic function. I plug in the limits b over a. This is delta v. And now all I need to find, R, the resistance. So what is the resistance? According to Ohm's law, the resistance is delta v, V at B minus V at A, absolute value, for the resistance divided by current. So V at B minus V at A, absolute value is right here. I divide by current I, and my final answer will be rho divided by 2 pi L, and then logarithmic function B over A. And of course, this is the same answer as we obtained by using this method. So those two are two different methods to find the resistance. I explain both of them because both of them are very useful.